Welcome back. In the previous sections, I once touched upon the moment where I presented it as a quantity that creates the angular acceleration of an object. If you remember, then for a constant mass, F equals m times a. So if you have a rod here, and this is its center of mass, and I apply this force to this point, then the rod will accelerate in this direction, and then you can relate force and the acceleration through mass. So F is in newtons, m is in kilograms, and a is in meters per second squared. You can also think of this mass as resistance to acceleration. If I take this equation and I rewrite it like this, A equals F over m, then you can see that for a certain force, a bigger mass gives you less acceleration. Your mass is in the denominator, so the bigger the number in the denominator, the smaller your A. And then vice versa, the smaller your m is, the bigger your acceleration is, assuming that you're not changing your force. A smaller number in the denominator will give you a bigger A. However, if I now have this situation where I apply this force here, then your center of mass will still accelerate in this direction, and the acceleration still has the same magnitude. But since the force is not applied to the center of mass of the rod, there is a perpendicular distance between the line of action of the force and the center of mass. That will create a moment that is clockwise, which is F times d, and that will also create a clockwise angular acceleration that we can denote with alpha. And then you have also learned that this moment, it also equals I times alpha. So again, m is the moment in Newton meters, then alpha is the angular acceleration in radians per second squared, and then this I here, that's the mass moment of inertia. And if you want to know the units of mass moment of inertia, then you can simply rewrite I like this. I equals m over alpha. So you will have Newton meters over radians over second squared. I can rewrite it like this, but remember, radians is actually meters over meters, so it's dimensionless. And so that means that you have newtons times meters times second squared. But remember, newtons can also be written like this: kilograms times meters over second squared. So this one is newtons, then times meters and times second squared. And so you cancel out second squared, and you're left with kilograms times meter squared. So that's the unit for your mass moment of inertia. Now the mass moment of inertia depends on the mass and mass distribution. So two things, mass and mass distribution. So it also counts how mass is distributed in the object. For example, consider two cylinders, cylinder A and cylinder B. Both of the cylinders have the same mass, so MA equals MB. Then both of them have the same radius, so let's say that this is RA and this is RB, and RA equals RB. And then both of them have the same length, so LA equals LB. But in case of A, the cylinder has equal mass distribution everywhere. But in case of B, the cylinder is hollow inside. It's empty inside. So all the mass is concentrated here in the edges. And now, if we say that this is our x-axis that goes through the cylinder, and the same thing here, this is the x-axis that goes through the cylinder. If we now measure the mass moment of inertia of the cylinder A and B about this axis x in both cases, then you will have IA here, IB here, and you will find that IA is smaller than IB. And that's because even though both of them have the same mass, MA equals MB, but in case of B, all this mass is concentrated further away from this x-axis. And now, just like mass was resistance to acceleration, the bigger the mass, the smaller the acceleration. If I now take this equation here and I rewrite it like this, alpha equals m over I, then you can see that the mass moment of inertia is resistance to angular acceleration. So for a certain moment, a bigger I would mean less angular acceleration for the object, meaning that it's harder to make the object turn when you have a bigger I. And then a smaller I will give you a bigger angular acceleration. So it's easier to make an object rotate with a smaller I. And now, here I have another exercise for you. I have a ramp here, and I have my cylinder A here, and also cylinder B here. And so you can imagine that in 3D, it will look something like this. This is your cylinder A, and this is cylinder B, and they are both at the same height. And now let's assume that I allow them to roll down the ramp at the same time. So my question is, which cylinder will reach the ground faster, A or B? Which one will reach this ground faster? Give it a thought first, and then let's talk about it in the next video. Thank you very much. Welcome back. So which cylinder will reach the ground first? I have a small Python animation here. So the green one, that's your cylinder A, and then the blue one, that's your cylinder B. The cylinder B is the hollow one. And like we discussed before, the hollow one has more mass moment of inertia compared to cylinder A. So if I run the animation, then you can see that the cylinder A wins. And we can see it one more time. You can see that the cylinder A rolls down faster. Why is it like that? The thing is that both of them have the center of mass in the middle of the cross section. Both of them have the same force of gravity because both of them have the same mass. In fact, let's just call it the weight. And now we can decompose this weight parallel and perpendicular to the ramp. So let this one be W parallel and this one W perpendicular. And now let's just say that MA equals MB equals M, because they're all the same anyway. So W equals M times G. And also, since RA equals RB, we can just say that it's R. That's the radius of the both cylinders. And that R is the perpendicular distance between W parallel and the ground. And so if we assume no slipping in the contact point of the ground and the cylinders, then the cylinders will only go down rotating, meaning that there will be no slipping between the surfaces of the cylinders and the ramp. The cylinders will only rotate down, and that will happen due to the moment, which equals W parallel times R. Now here I need to point out that this cylinder rotates because there is static friction force that is between the cylinder and the ramp that points in the opposite direction. And when there is static friction, then that means that the wheel is rolling down without slipping. So there is no sliding between the wheel and the surface of the ramp. The cylinder only goes down due to rotation and not due to sliding. If there was no friction force between the cylinder and the ramp, then the cylinder would still go down, but it wouldn't rotate, it would just slide down. But since there is this static friction force, you have a moment that makes the cylinder rotate. And that moment is the same for both cylinders, because both cylinders have the same W, which means that they have the same W parallel and W perpendicular. They have the same R, so they must have the same M. However, IA is smaller than IB, meaning that there is less resistance to rotation in case of A compared to the case of B. And that means that the angular acceleration, alpha A, is greater than alpha B. Because of that, the cylinder A picks up rotational velocity faster than cylinder B. And that's why, in the end, cylinder A will win the race. Cylinder B will stay behind because it has more mass moment of inertia, which means that it has more resistance to rotation. And by the way, since the moment is taken about this point IC that we call an instantaneous center of rotation, the mass moment of inertia is also with respect to that location, and not with respect to the center of the cylinder, but with respect to that IC location. However, it doesn't change the fact that the hollow cylinder still has more mass moment of inertia, even with respect to this IC point, compared to the other cylinder that is not hollow. More on that in dynamics part 2. And now I want you to know that there is another kind of moment of inertia called the area moment of inertia, or simply IA. So A stands for area. This is a completely different thing. It's a different concept. It tells you how hard it is to bend something. So let's say that you have two beams. One is the I-shaped beam, and the other one is a T-shaped beam. As you can see, they have different cross sections. If we assume that both beams have the same dimensions, except that the T-beam misses that lower plate here that the I-beam has, and they both have constant mass distribution inside, they're made of the same material, then the area moment of inertia for the I-beam is greater than the area moment of inertia for the T-beam. It means that it is harder to bend this I-shaped beam compared to the T-shaped beam. So let's say if I take these two beams and I look at them from the side, so this red triangle, it's this one here, and this red triangle, it's this one here. And now if I apply the same force on top of both beams, then the T-beam will bend a lot more than the I-beam. And that's because the I-beam has greater area moment of inertia for its cross-section compared to the T-beam. And the area moment of inertia is resistance to bending. Since the I-beam has more area moment of inertia for its cross-section, it has more resistance to bending, so it bends less. The T-beam has less area moment of inertia for its cross-section, so it can resist bending less. So that's area moment of inertia. However, when we talk about the moments and its relation to angular acceleration, then this one here, that's mass moment of inertia and its resistance to angular acceleration. Thank you very much. Welcome back. Here I have another situation. I have a rod and I have the same force applied to both of the tips of the rod, but in different directions. Since both of these forces are the same, they will cancel each other out, and so there is no acceleration for this center of mass. The acceleration is 0 meters per second squared. This point, this center of mass, will stay where it is. It's not going to go anywhere. However, you do have a moment. Let's say that the length of the rod is d. It means that this one is d over 2 meters, and this one is d over 2 meters. Let's call this tip A, and this one tip B. That means that the moment from point A about the center of mass, that's F times d over 2. And that would be clockwise. It would be in this direction. And then the moment from point B about the center of mass, well, that would also be F times d over 2. And this one would also be clockwise in this direction. And so the net moment about the center of mass would be ma plus mb. So you would have F times d over 2 clockwise plus F times d over 2 clockwise, and that will give you F times d clockwise. This is a special kind of moment called a couple moment, and all it means is that a couple moment only makes an object rotate. The center of mass of this rod will not accelerate anywhere because the forces cancel each other out. Remember, F net equals mass times acceleration. But if F net is 0 newtons, because what you essentially have here is F minus F, which is 0 newtons, then that would also mean that your acceleration is 0 meters per second squared. So that's why the CM will not accelerate anywhere. But because the both forces are positioned in equal but opposite distances from the CM, and they themselves point in the opposite directions, they will both create the same moments in the same direction. So in this case, both will be clockwise, and thus the object will only accelerate angularly. It will only rotate about the center of mass faster and faster, clockwise, while the center of mass stays in one position. Also, as you have seen, instead of computing this net moment, which is your couple moment, instead of getting this net moment traditionally, like we have done here, in case of a couple moment, you can just take that force F and you can multiply it by d, which is the total perpendicular distance between these two forces. So when you have a couple moment, then you can simply calculate it like this. Just take one F, take this d, the perpendicular distance between the two forces, and your couple moment will be F times d. That's only valid for the couple moments though. And also, if you don't want to draw these force arrows applied to the rod all the time, then an equivalent way to draw this is like this. You have this rod, you have this center of mass here, and instead of force arrows, you just draw this couple moment representation here, where you draw it in the direction of the rotation of the object. And then you write here m equals F times d. And by the way, a moment is also a vector. It means that it has a direction. And the direction of a moment is perpendicular to its rotation plane, either like this or like this, depending on the right hand rule. So if you take your right hand and you rotate your fingers in the direction of your rotation, then your right hand thumb will tell you the direction of the moment. In this case, it's this one, and in this case, it's this one. These are your knuckles, and you don't see the fingers because they are behind the hand. And your right hand thumb points in the direction of this moment. In 2 dimensions, a counterclockwise moment, which is this one, its vector direction and the right hand thumb points out of the screen towards you. And this is how we draw that. It's like the tip of the arrow. And then a clockwise moment, which is drawn like this, its vector direction points into the screen away from you, just like your right hand thumb points into the screen. And this is how we draw it. It's like the back of the arrow. So if I have an arrow here, then this cross, it would be this one here, and then this tip, it would be this one here. But of course, you would be looking at it either from this side or from this side. And now I have a Python animation here. I have a rod here, and I will be applying a couple moment to this rod. You can see that right now, the couple moment is 0 Newton meters. This is its mass moment of inertia. Alpha is the angular acceleration in radians per second squared, and then omega is the angular velocity, which is radians per second. And now all of a sudden you see that you have a moment, you have angular acceleration, so your omega is increasing. And then all of a sudden your moment is 0, no angular acceleration, and your omega is constant. And then after some time you have a negative moment, you have negative angular acceleration, and your omega is decreasing, and it's decreasing until it starts rotating in another direction. And then after some time your moment again is 0, so no angular acceleration, and you have constant omega up until you again have a positive moment, positive angular acceleration, and your omega is increasing until it reaches 0 radians per second. Note that just like a body is at rest or at constant velocity, if there is no force, the body is also rotationally at rest, or it has constant angular velocity if there is no moment. Force causes acceleration. In other words, it causes the change of velocity with respect to time. And then moment causes angular acceleration. In other words, it causes the change of angular velocity with respect to time. So in other words, this alpha, it's nothing else but d omega dt. It's the time derivative of the angular velocity. And so you see that this is your mass moment of inertia, and when I apply the moment, then this rod starts rotating faster and faster. However, let's now increase this mass moment of inertia. Let's keep the moment the same, but let's increase the mass moment of inertia. So now your mass moment of inertia is 60 kilograms times meter squared. And now all of a sudden, when I apply 40 newton meters of moment, then it's harder to start making this rod rotate. And so as a result, it doesn't rotate that fast. And now when I apply a negative moment, then again, it's a lot more effort to make this rod rotationally stop and make it rotate in another direction. You can see that it's all a lot slower, and that's because your mass moment of inertia now is greater, but the moment that you're applying to this rod is still the same, and that's why it's just a lot harder to rotate this rod. Because remember, the mass moment of inertia is resistance to angular acceleration. Because of the fact that your moment stayed the same, but your I is greater, your alpha is smaller, so during the same amount of time, your omega will also end up being smaller. But now, let's keep I the same and let's increase the moment. Now my I is 60 and now the moment is 180 newton meters. So you can see that now the rod really starts rotating very fast. And now the rotation is constant because the moment is 0 newton meters. And now after some time, the moment is negative 180 newton meters. So the rod obviously becomes slower and then it starts rotating in another direction up until the moment becomes 0 newton meters again. And so you have constant rotation. And then after some time, your moment again becomes positive, and so the rod will slow down because its omega will go towards 0. And now, in the next video, I want to give you an exercise that I used in one of my autonomous car control systems courses in order to better explain the moments. I think that this little exercise will help you better understand it. Thank you very much.